This is Unit 7, Lesson 3, Independent Events. Independent events occur when one event has no effect on the outcome of the other event. So what we're going to do today is we're going to look at whether two events actually have any impact on one another and to mathematically determine if those two events, the probability of those two events, are actually independent. The equation we're going to use says we're going to take the probability of A and B, and it should equal the probability of A times the probability of B. So when I put the numbers into this equation, I should find that if those two things are equal to one another, the events are independent of one another. If when I put all of the numbers into this equation, the numbers don't come out to be equal to one another, then the events are not independent. There are a lot of events in the world that are not independent. So the first example says a basket contains one pair of socks in each of the following colors: blue, brown, red, white, and black. Each pair is folded together in a matching set. You reach into the basket and choose a pair of socks. You replace this pair and then choose another. What is the probability that you choose the red socks both times, and are these independent events? Well, the first thing you want to do is you want to calculate, hey, what's the probability if I reach in and I get a red sock? Well, there's one pair of red socks, so the number of elements for red socks is one red sock. And the number of elements in the sample space is 1, 2, 3, 4, 5 pairs of socks. So what we want to do is we want to determine, is the probability that I get a pair of red socks independent from the probability that I get a pair of red socks? Now, before we even do this, I can tell you that these are going to be independent because it says in the middle of the problem, it says you replace this pair and then you choose another one. That's key. When you're drawing elements, whether it's a pair of socks out of a drawer, cards from a deck, a marble out of a jar, if you take that marble out and then you put it back in, you've ensured that those are independent events. When you take that marble out, or in the case of this, if you take that pair of socks out, you've changed it, and now event 1 has an impact on event 2. So if I were to take this pair of red socks out and put them on, and then try to calculate the probability that I'll draw another pair of red socks, I've changed it because there aren't any red socks left in the drawer. I've taken them out. I've changed how many things are in the sample space. I've changed how many pairs of red socks there are in the drawer. So the key sometimes is just recognizing that if elements get put back into the situation, then they no longer have an impact on the second occurrence of something happening. So let's look at this. We've got the probability of a pair of red socks is 1 out of 5 times the probability of another pair of red socks. Well, when I multiply these things together, they specifically equal the probability of me getting a pair of red socks and getting another pair of red socks. So I know that these are independent of one another. Example 2 says a card is chosen at random from a deck of 52 cards. It is then replaced and a second card is drawn. What is the probability of choosing a jack and then an 8? And are these independent events? Think about what I just read. Do you need to do the math to calculate that these are independent events? No, you don't, because it says then replaced and a second card is drawn. So whatever you draw the first time is going to get put back, and so we're not going to have an impact on the event of the second card being drawn. But we want to do this mathematically, so we calculate the probability of drawing a jack. How many jacks are there in a deck? Well, there's 4 of them. So there's 4 jacks in a deck out of 52 cards in a deck. And that will simplify down to 1 over 13. And the probability that you draw an 8, how many 8s are there? Well, there are 8. There are 4 8s in the deck out of 52 cards. Also simplifies to 1 over 13. So to calculate the probability that you'll draw a jack and an 8, so, wow, How many jacks are there? There's 4. How many 8s are there? There's 4. So we want to put those two things together. So actually to calculate the probability of a jack and an 8, is to multiply those two things together. Well, if I just took these two things and multiplied them together to make this, then I know that if I put them in to this equation, the probability of each one of these events happening, they're going to equal one another. So these events are independent. Now, it's going to get a little more complicated than that. There are going to be things that aren't as clear, and you're not going to be able to say, oh, well, they put that back in there, so those elements are independent of one another. They don't have any effect. Sometimes we get a nice little chart like this right here. So we've got a two-way frequency table. A group of 110 students were surveyed. That is not 110. Yeah, that's 110 students. 110 students were surveyed to determine which animal they preferred as a class. Let event C be the probability. So C is the probability that they like cats. And let T be the probability that a student is in the 10th grade. So what we want to do is we want to determine if liking cats is independent of being in the 10th grade. So we're going to do this by, let's total all these things up. We know there's 110 students. So 25 9th graders and then 20 10th graders. And there are 28 11th graders, and there were 37. Let's double check and make sure those numbers add up to equal 110. They do. And then people who like dogs, there were 20, 16, 22, and 30. So there were 88 people who liked dogs, and a considerably smaller number of people liked cats, but there were 22 people who liked cats. So we're going to use this table to determine if the probability of liking cats is independent of the probability of being in the 10th grade. So the first thing we want to do is we want to calculate the probability that they like cats. So we find the number of people who like cats. How many people like cats? 22 people like cats. And that's over the 110 people that were surveyed. And that's going to simplify to 1/5. And then we want to find the probability that someone is in the 10th grade. Well, how many 10th graders are there? There are 20 10th graders out of 110 people who were questioned. And that simplifies to 2/11. Then what we need to do is we need to find that intersection, that and, where cats and 10th graders overlap. So 10th graders is here. Cats is here. Where do those two things intersect? They intersect at 4. So the probability that someone likes cats and they're in the 10th grade is 4 out of 110, which simplifies to 2/55. And then we're going to set up the equation. The probability that someone likes cats and is in the 10th grade should equal the probability that someone likes cats times the probability someone's in the 10th grade. And that will tell us if this statement comes out to be true, then we know that these are independent events. So we calculated that this is 2/55, and the probability of liking cats is 1 out of 5, and the probability of being in the 10th grade is 2/11. And the rules tell us multiply across the top. 1 times 2 is 2. Multiply across the bottom. 5 times 11 is 55. 2/55 does in fact equal 2/55. So these are independent events.